Hi everyone, welcome to Control System lecture series. In this lecture series, we are going to see 45 different lectures about control systems. So we are going to see how a control system is mathematically modeled, how a control system is numerically solved, and how a control system is visually plotted. So this lecture series is going to cover these three things, and we are gonna see a lot of examples, we're gonna see a lot of illustrations, and we are gonna see a little bit of coding to go with what we discuss in theory. So we'll be using mostly MATLAB or Jupyter Notebook for our programming illustrations, and for plotting we'll be using certain open source tools which will be available for you in the coming lectures. So you can use those open source tools and you can make practicals, or you can practice this lecture along with the course. Well, so today's class is going to be an intro class about control systems, and we are going to see three important things, which are: what is control system, what is the definition, why we need control system, what is the use of a control system, and what are some of the introductory properties. When I say introductory properties, that is like what are the properties that defines control system, and without that your control system cannot exist. So here we have two words in our control system: control and a system. So we're going to see separately what a control is and what a system is, and put together what these two words mean, so that we are going to learn an entire subject. We're going to see an entire course semester on this subject. So the word control, it indicates that you're controlling something. So a control of working of the system. So the important thing here is you need to understand that what is intended to be controlled. It's not the climate, it's not the certain other factors, it is only the working of the system. So a system exists, and the system's working has to be monitored and controlled from time to time, which brings us to this domain known as control system. So in your control, you are having speed, accuracy, efficiency, and stability. So I would say these four parameters are very vital and are essential to control the system functioning. Now coming to the system, what you have on the right side is a system works with an input to produce an output. So you have an input entity or an input variable or an input system which is sent to your system, and your system processes this input and it gives you an output, just like your CPU, central processing unit. But we are not there yet. So we are still, when I say control system, there is always a confusion whether I'm talking about an analog control system which doesn't make use of the computer, or am I talking about a digital computer or a digital control system which makes use of a digital computer. So in this course we are primarily focusing on analog control system. So this is a control system before the invention of your computers. Good. So now an example, and wonderful example of an analog control system is your voltage stabilizer at home. So the functioning of an voltage stabilizer is very simple. So the system is your stabilizer, which is set at 230 volt. So what it does is, whatever is your input voltage, it is, as far as the input voltage is concerned, when it goes beyond 230, when it goes above 230, the voltage stabilizer stabilizes it or brings it down to 230. The output of the stabilizer will be 230 for high voltage. The max voltage that comes out of the stabilizer will not be more than 230 volt. Thereby, it is protecting your equipments which are powered by this 230 voltage. So the voltage stabilizer in this case can be considered to be, it has accuracy and it has the stability. Similarly, for other control systems, other examples which we will be seeing, we will also see why the speed, or what we call is the speed or the response of the system, as well as the efficiencies, are important. Now we will see what is the need for a control system. Since we are doing this intro class today, it's good to see what are some of the things that makes control system essential for our daily life. Control system may not be a direct express technology, but it is always an implied technology in that it is used inside many of our equipments and components of daily life. So the certain things that make control system very essential is the first being the safety. So most of the control systems are a fail-safe system where it prevents the system from failing and harming an individual or causing certain accidents, and it can prevent it very efficiently. The second is automation. So for automation, it's best to see that the control system we are talking about is a pre-digital era, or it is considered to be before computers, or BC. A technology BC is always called as before computer. So when we say it is a BC technology or before computer technology, we are talking about analog systems. So this subject, like I said earlier, it is an analog control system. So the automation we are talking about is for making things run by itself, or making certain tasks, routine tasks, to take place on its own without user intervention. Convenience is another thing that goes hand in hand with automation. So when you automate certain things which are otherwise done by human beings, the convenience automatically becomes a factor that control system is used for. Then the last is the technology evolution. So when we evolve the technology, so from we have BC, before computers, to now after computers, we are looking for evolution of technology that makes again life convenient for us. And here again your control system. So if you look at example 2, the bike self-starting mechanism is one of prime example of how a convenience is achieved. Before a self-starting, we used to manually use pedals to start our bikes and motor vehicles. Now you are having the self-start mechanism whereby just click of a button, your vehicle is ready to go. So that is an example of convenience. And for technology evolution, you have digital control system. So when I talk about technology evolution, you are always having a control system with a computer. So that is your technology evolution. So these are the four areas, and I have identified a fifth area, which is I'm calling it as an etc. because this is a list that keeps adding on. So for now, I'm stopping with these four, and soon in our other classes, I'll introduce to you some more needs for control system. So now we will see some introductory properties of control systems. So in this, we are going to just touch the surface of control system with what is a feedback in control system, what is a dynamic control system, what is time independent or dependent control system, and finally, what is a linear time invariant system. So for the last property, we are having two properties which are integrated into a single entity. So that is linearity and time invariance. So we will see what these two are separately, and then why they are important for control system, and why they are integrated as an LTI system. Now for feedback mechanism, you can have to be either open or closed. You can have it to be either static or dynamic. Then you have independent versus dependent. So I would say I would go for the word versus then or. So I'll just replace these two. So open versus closed, static versus dynamic, and independent versus dependent. And for linearity, you have linearity versus non-linearity, and time variance versus time invariance. So we will be seeing all this as an introductory property of control system. However, for today's class, I think I'll have enough time to discuss the first three. The last property of LTI system would take almost an hour to illustrate and explain. So I will keep it for our next lecture. So we'll see today what the first three properties mean in our control system. And we are going to see all these three properties at only introductory level without going in depth. So now, what is the first property that we are going to see? It is called as a feedback system. Very, very important property in control system, because In order to control your system, you need to have either an open feedback or a closed feedback. Now, an open feedback is a one where your output never controls your input. So what does it mean when you say an output never controls input? It means your output never meets your input. So the output that comes after processing from the system is not aware of what the input was, and it will never, and the input that is giving the output or producing the output through the system will never know what is the output that it is producing. And a typical example of your open loop feedback is your switch in your home. When you switch on, let us say, to turn on light, your input is the current that is going to flow to the switch, and your bulb that is going to turn on is your output, and the switch here is your system. So this is an open system because the output bulb and the input current, they are never going to be crossing. So if the switch is not on, then output and there is no bulb light, and when the switch is on, then the bulb is on or the bulb light is on. So there is no, when I say they don't meet, it's like they don't communicate. There is no communication between input and output. A closed feedback system is an opposite for open loop feedback, where the output communicates with the input or output controls the input. So how does it look? Let us see. So this is how a closed feedback loop looks like. Here the output is communicating with the input, and based on this communication, the system changes itself. The system will change according to how this feedback loop asks it to behave. The system behavior is dependent on the feedback loop. And perfect example of your closed loop system is your temperature control in AC cooling. So let's say the outside environmental temperature is 30 degree. Your AC mode will be at strong or turbo mode. When the outside temperature becomes 25 degree, the same AC will adjust itself to normal mode. So this way your air conditioning is adjusting to the output temperature. This is an example or a perfect example for or a daily application for closed feedback system. This is just an intro level explanation for a closed feedback system. We are going to see plenty of mathematical derivations on feedback systems in the coming lectures. So for the next property, we have a dynamic system. So let us see what is a dynamic system. So to understand a dynamic control system better, let us go back to this XY graph where your x represents the time. And here it is very much important that you note, for a control system, always your x-axis is time. The y-axis can be any component. It can be an voltage, it can be speed, it can be amplitude, it can be current, it can be resistance, it can be time, not time, sorry, it can be the time dependent variables, like it can be the response time, it can be the latent time, it can be the quality of service. So y-axis can be a plenty of variable, whereas your x-axis in all these cases is going to be just time. So this way we call a dynamic system, or we call all the control system that we are going to encounter in this course, has a time domain control system. So I'm not using the word control in everywhere, because when I say a time domain system, it is applicable to the system, but since we are saying that in this control system class, it is a time domain control system. So when I say our systems are always time domain, it means the x-axis of our system is always time. Now the y-axis change with time. So what happens is, uh, the definition of a dynamic system is the control variable. So I'm going to replace the other with control. The control variables change with time. So that is what your dynamic system represents. So now the control variables change with time, meaning the system is, the control variable is changing with time, means your system is adaptive, or your system is heterodyne, or you can say your system is no longer a homogeneous system. So what it is a heterogeneous system, or it is an adaptive system. So a dynamic system is a one where your variables change with time, and a perfect example of your dynamic system is aircraft control. So let us see what happens is, the aircraft control system, which is inside an aircraft, behaves differently at different depth of altitude. So at 0 feet, it may be having certain set of control, and at 10,000 feet, it may use another set of control, and at 20,000 feet, it may have another set of control. So this is a good example of dynamic system. And aircraft control systems, when the safety is a high priority, because it is an aircraft and it is very much prone to this, the lack of safety measures will lead to a big time damage. So we are very much interested in control system of aerospace and aircraft control. So throughout this lecture, you will be seeing a lot of examples on which are based on aircraft controls. Good. So here you can see, for 0 feet, my settings will be at A, and for 10,000 feet, my control variable settings will be at B, and for 20,000 feet, my control system settings will be at C. So this is an example of your dynamic system. Now, what is an example of your static system? An voltage stabilizer. So we have seen already, the opposite of a dynamic system is your static system, where your control variables don't change with time. A simple voltage stabilizer that we have seen in the beginning of this class is a perfect example of your static system. Next, we will see what is time dependent versus time independent property. So, a time independent property defines the same performance at any instant of time. So, what it means is if I am taking a system which is working from 0 to 60 minutes, let's say, so if I am measuring the performance of the system at 15 minutes, and if I am again measuring the performance at 30 minutes for the same input, I will be getting the same output. So, for a time independent system, the output of the system is not affected with change in time. When the system is operated. Good. So I'm running the system at 15 minutes or 30 minutes or any time between 0 to 60 minutes. I am going to see the same performance or I'm going to see the same output. So this is a classic definition of a time independent system. An example of a time independent system is your household fan, a household motor, or any kind of rotating device because the speed of the fan is the same every day. So if you are having a fan which is having a specification of 60 RPM, then the speed of the fan is going to be 60 RPM. Even an analog clock. So it is driven with a crystal and its oscillations are going to be the same every day. So the same speed or the same rotation happens every time, every day. There is of course a wear and tear of the fan over a period of time, like say a year or 2 year. But the control system in question are mostly in minutes. So we are not looking at anything beyond a 1 hour time frame. Most of the systems which is analyzed by us or designed by us can be tested for a short duration of time. A time dependent system is the opposite of this independent system, and it is not very significant in control system because most of the systems we will be studying are time independent systems. So a typical example of your time dependent system I would say is your solar panel. So it depends depending on the sunlight or the temperature of the day, the solar panel or the solar watch or the solar calculator, the performance will vary. So a typical example is a solar panel or a solar device. I can say any solar electronic device is a good example for a time dependent control system. So I think that is for good for our intro lectures today. We have seen a few things that will serve as a good introduction to control system. We are not starting the linear time invariant systems today. That will be the focus of the next lecture. So to summarize what we have seen today, we have seen three things. What is control system? What is the need for control system? And what are some of the introductory properties of a control system? And your keywords for today that we have seen is feedback, open closed, dynamic static system, time independent dependent systems. Then I think so that pretty much gives all for today's class, and we have seen a lot of examples. I hope the class is clear. So it gets little more difficult as we go along, or little more mathematical in the coming lectures. So please continue watching the lectures. Any doubt you can ask us. So I'll see you soon for the next lecture. Thank you.